Throughout this course, we'll be using a computer programming language to help us analyze and understand data. Now, our programming platform of choice is the powerful programming language known as R. R is the leading tool for statistics, for data analysis, for machine learning, and it's more than just a statistical package. It's a programming language, so you can create your own objects, your own functions, even packages. Now, speaking of packages, there are over 10,000 cutting-edge, user-contributed packages that are available online at CRAN. That stands for the Comprehensive R Archive Network. Now, why do we use R? Well, a couple of reasons. First of all, it's free. That means anybody, anywhere can access it. It's open source, meaning anyone who has code can see exactly what they're doing. And it explicitly documents the steps of your analysis. R also makes it easy to correct and to reproduce your work. You can use it anywhere on any type of operating machine or any operating system. And it even lets you communicate with other programming languages like C++ or Java or even Python. Now, you can interact with many data sources, so spreadsheets like Excel, even other statistical packages like SAS or Stata or SPSS. We can import simply by pushing the Import Dataset button in RStudio. Now, R has a large, active, and growing community of users, many of whom are experts in their respective fields. Now, other statistical packages, on the other hand, are limited in their ability to change their environment. They're going to rely on algorithms that have been developed for them with more limited programming flexibility. In fact, the way they approach a problem is often constrained by how their employed programmers thought to approach them. R, on the other hand, you're the programmer. You get to program any solution any way you choose to. And lastly, they cost money. Now, you may ask, what about programs like Excel? Well, it has several benefits. First, people are super familiar with spreadsheets, and it's easy for them to do minor data analysis on a small, clean data set. In fact, you can do quick analysis of small data sets. It's easy to get a quick and dirty look at the data and do a simple one-time analysis. With spreadsheet programs like Excel, a lot is accomplished through mouse clicks, which is a great user experience in the moment. But if you want to recreate your work with new data, it can be time-consuming and often monotonous. With R, you just load a new data set and you run your scripts again. Now, spreadsheets also have drawbacks. It takes a long time to manipulate data in a spreadsheet. In fact, even simple commands like taking the mean or the log of your data become extremely difficult. In R, however, it's a one-liner: mean data, log data, and we're done. Now, if you're starting with spreadsheets like Excel, that's okay. But R is faster, it's more powerful, and if you start with R from the beginning, you'll already be prepared whenever you find yourself wanting to go to a more complicated analysis that you're not able to do in a spreadsheet environment. With R, everything is accomplished through code. You load your data into R, you explore it, you manipulate it by running scripts. It's easy to reproduce your work on other data sets because all the data manipulation and the exploration is done with the code. It's going to be simple for you to redo your work on a new data set. Now, since you're working with actual code, you can see where the problems are and you can fix them. It's also easy to share your work and have others add to what you've already done. And if you still have questions, you can get help online. Often you can post your code and show exactly what you're doing and ask very specific questions to get feedback from the community. In fact, most of the time, when you get help online, people will post the exact code that addresses your issues. There's a great website, stackoverflow.com, which is a community of roughly 7 million programmers, just like you, helping each other with code. Now, you can load data into R, and it doesn't matter where your data is, what form it's in. In fact, we can load CSV files. Now, for the first time, it'll ask you to install required packages. Just say yes. Let's do that now. The command install.packages read R installs the read R packages into RStudio. Library read R is going to call that package to the forefront. Here, I've created a data set called shoes, which I've stored on my desktop. And I'm using the read_CSV command to find that. And then I can use the command to view shoes so that it actually shows it in R. So instead of actually typing the code, we can also go in R and click on that, and we'll do that in a moment. Now, through the use of packages, R is a complete tool set and can do much more than Excel when it comes to data analysis. As I mentioned earlier, we've got over 10,000 packages available. So regardless of what type of data you're working with, R is going to be ready to handle it. And if it turns out that you need a package that you don't already have, you can install it. R is not without its drawbacks. First, there's a learning curve, and there's minimal graphical user interface. It can also be easy to make mistakes that might seem correct intuitively. But don't worry. This course has been designed to walk you through that process and build your programming confidence. Let's look at an example in R where we're going to get an error. Here we've set x equal to 2, and we want to set y equal to 2 times x. How do we do that? Well, first, notice we wrote just y equals 2x, but we get an error in R. Unexpected symbol in the y equals 2x. What does it mean? Well, we've got a 2 next to an x, and R doesn't really know what to do with that. Okay, what if we try parentheses? Y equals 2 parentheses x. Well, again, we get an error. Attempt to apply non-function. The problem there is that parentheses looks like 2 is a function, and we want to apply x to use inside of that function. The correct way is y equals 2 asterisk x, or star x. The asterisk is used for multiplication, and R recognizes that, correctly multiplies 2 by x to give us 4. Now, one of the most useful features of R is its ability to handle and manipulate data. Let's start by double-clicking on the R icon to open the R console window. This is in RStudio. Now, in its most basic functions, R works much like a calculator does. I'll demonstrate, and you can follow along now or later. Open RStudio and locate the R console window on the left, or the lower left if you have 4 panels. Now type immediately after the greater than prompt the expression 3 plus 5 and hit the return key. Now this command, greater than, indicates that R is ready to receive your command. Writing an expression such as 5 plus 3 or 5 plus 5 or 20 plus 20 and hitting the return key is going to send that expression to be executed. Let's use R to actually explore some data, but first we have to input it. Here we're going to assign x equal to 3, and if you type x equals 3 and then x by itself, R lets you know that it recognizes that variable as 3. Likewise, let's assign y equal to 5 and check that yes, y equals 5. What if we wanted to add those two things together? Well, we can actually write x plus y, and R recognizes that we want to add 3 plus 5 and returns us a value of 8. We can do other types of manipulation like multiply x and y to get 15. We can divide x divided by y to get 0.6. We can even assign x divided by y to a new variable, call it z. So here we're setting z equal to x divided by y. And notice when we call z, R recognizes it as 0.6. Now the function c combines its arguments and produces a sequence. We often use this command to define a small data set. C allows us to define a group of numbers as a set, and that's great because then we can plot them. Here's an example. Let's look at C of 3, 0, 10, -4, and 0.5. Notice when we enter this command in R, it gives us those numbers together as a set. Now the function C is an example of an R function. In this example, a sequence was created and it was sent to the screen, but we didn't save it. If we want to create an object that we want to use later, then we have to save it and we have to give it a name. For example, if we want to save the vector of data under the name widget, then we'd write the following expression at the prompt. Widget equals C 3, 0, 10, -4, 0.5. And let's type in widget to see that, yes, R recognizes what our set is. What if we wanted to add 2 to everything in widget? Well, we can actually do widget plus 2, and R recognizes that and adds 2 to each one of our elements. What if we wanted to multiply widget by itself? Again, we can multiply widget times widget, and we get the square. Likewise, we can use the command widget hat2, which says I want to square widget, and we get the squared values there as well. Now, you'll usually want to save your work, and to do that, we'll need to open a script file. Go to File, New File, and then R Script. That'll open a panel in the upper left of your screen. Now, in that script window, we can try the code you see here to generate our first plot. Let's let x equal to 1, 2, 3, 4, and 5. And notice here we're using the C function to combine those numbers into a set. Likewise, we're going to let y equal to 1, 8, 27, 64, and 125. Using C again, we combine that into a set, and now we want to plot x and y. Here's our first plot in R, and how we get it is first highlight the script and then click the green run arrow. It should give you this following plot. Doesn't really tell us much, but we can actually add titles and labels to get a much more visual picture. Go back to that plot XY command, and we're going to add the following to it, a title. We use that with the word main, setting main equal to, I don't know, our first R plot. That needs to go in quotation marks. Next, we want to label our X and Y axes. And we do this with the command xlab, short for xlabel, equals the integers from 1 to 5, also in quotation marks. If we label the y-axis, ylab, we can label that as integers from 1 to 5 cubed. And make sure you close that parenthesis, otherwise you're going to get an error. If we run this line of code, notice we get the same plot, but now our x-axis and our y-axis has been labeled, integers from 1 to 5, integers from 1 to 5 cubed, and we've got a beautiful title to go along with our plot. Now, R comes equipped with lots of built-in data sets and various packages. Here's how you might install a package. With code, we'd actually type into our script file, install.packages, open parentheses, and put the library datasets in quotation marks. Next, we'd use the library of datasets, which is going to bring that dataset library to the forefront. And out of it, we want to pick up the data faithful, and we want to plot that data. In the lower right corner of RStudio, you should also see 5 tabs. So Files, Plots, Packages, Help, and Viewer. We can also install a package this way. Click on Packages. Now, just below the word Packages, you should see the command buttons for Install and Update. Click on Install. When a window pops up, type the name of the package in the space for the packages, and then press Install. The package will automatically update to your computer. From your R script, type and highlight library datasets. You can run that line of code by clicking the Run button or just your selected lines. This loads the dataset library. Now, the Old Faithful geyser data gives the waiting time between geyser eruptions and the duration of eruptions for the Old Faithful geyser in Yellowstone National Park in Wyoming. To bring that data set up, let's run data faithful and plot faithful. Here you see the first plot of the Old Faithful data with eruptions on your x-axis and waiting on the y-axis. Doesn't really tell us much, but we know how to add a title to it, right? So let's do that now. Let's set main equal to Old Faithful eruptions in quotation marks. Here's our updated plot. It looks a little nicer. If you wanted to actually view the data set, we could just type faithful and it'll output what's in that file. Notice here, faithful has two columns. The first column is eruptions and the second is waiting. Both of those are in minutes. What if we wanted to label that? Right? So we've got eruptions and we've got waiting, but we don't know that it's time and we don't know that it's in minutes. Well, in that case, we would change our X and Y label. Let's plot that now. Here's a plot of faithful with our title, Old Faithful Eruptions. And now we've set our X lab equal to eruption length in minutes, and our Y lab equal to wait time in minutes. Notice what we've also done here is change the plot character. So we've set our plot character, or PCH, equal to 20. This actually gives us a darker point so that we can better see our data. When we run that code, we get an updated plot. Old Faithful Eruptions, so a great title. Our X and Y labels are accurately labeled with minutes. And we see our plots that really sort of jump out of the screen at you. Now, what if you wanted to change color on that plot? You can do that in R as well. Take that same code, and now we're going to add the color red to say we want our plot points to show up in red. The command we use for that is COL equal to red in parentheses. And here you see the updated plot. Now, a histogram is a plot that lets you discover and show the underlying shape of a set of continuous data. So we can also inspect the data for outliers and for overall spread. To get a histogram, we count the occurrence of each value of the variable, and then we plot the number for each count, which is the frequency, on the y-axis. We can display the frequencies or the percentages in a histogram. Here's an example, histogram of our faithful data with waiting times. So notice you see our bin size goes from 40 to 45, 45 to 50, and in each of those bins you have the frequency on the y-axis. If we look at our histogram, we can actually see the counts that are used and the bin size, and that comes out when we run the following code. Histogram of faithful waiting, but now plot is equal to false. Notice here, this is telling us where the breaks are. The breaks are at 40, 45, 50, 55, 60, and so on. Also, histogram faithful waiting, plot equal to false. How many counts are in each bin? Well, that's what that code gives us. There are 4 counts in the bin that starts from 40 to 45. There are 22 counts in the bin that goes from 45 to 50, 33 counts in the bin from 50 to 55, and so on. Now, histograms are super flexible. They even let us change the size of the bin. What if we wanted to create a bin size of just length 1? So 40 to 41, 41 to 42. Here's how we do that in R. We take the histogram command, hist, and now we're going to set breaks equal to a sequence from 40 to 100, which is the length of our data, by equal to 1. So that tells us how many steps we want to have from 40 to 100. So we want to step in increments of 1. Here's the output of that. If we choose not to look at the plot, we can again look at the counts and the bin breaks. Notice here, our bins go from 40 to 41, 41 to 42, and so on. And then you see how many values lie inside those bins. So for example, in the bin from 40 to 41, we've got no points in there. Same from 41 to 42. But notice from 42 to 43, a value shows up there. Here's a histogram of that with bin size equal to 1. And you can now start to see the shape of the data. Right? There appears to sort of be 2 mounds in our data, and we can also see the spread. Minutes start around 40 as the lowest waiting time, up to not quite 100 as the highest waiting time. So it gives us a nice idea of the spread, and we can also see the times at which more of the waiting occurs. Now, a QQ plot is quantiles of our sample plotted against quantiles of a proposed distribution. In this case, the default is the normal distribution. If all of our points in a QQ plot fall on a straight line, this tells us that the quantiles of our sample are consistent with the quantiles of the proposed theoretical distribution. Let's do an example of a QQ plot. Here we're going to simulate normal data. So x equals random normal 300 points. And I want to do a QQ norm of x with a plot point size or plot character equal to 16 and add a QQ line to that. Here's the output that we get. Notice our simulated data, which are the points, and the line is exactly where a normally distributed data set would fall. Our data set is pretty close, which makes sense because we simulated it from a normal distribution, so it should be pretty accurate, plus or minus a little bit of error. What if we wanted to do a QQ plot of our old faithful data to see if our faithful data had a normal distribution underlying it? Well, the code we use for that is QQ norm of faithful and waiting with a plot character equal to 16. The CEX command, set equal to 0.5, says that the plotting symbols will only be half of the default size. We could add the QQ line to that, and here's our output. Whoa, look at that. Oh, we've got some curvature happening here. This data set doesn't quite appear to be normally distributed. It falls pretty far away from the normal distribution line. What if we had a smaller sample size of data that we knew was normally distributed? So now we're simulating random normal and doing a QQ norm on a size of 30 points and adding a QQ line to that. Here I want you to see that there's still some variability in the data, even though we're simulating it from a normal distribution. Notice though, as that sample size increases, here we've got a random normal size sample of 100, we get a lot closer to the true line, but it's not exact. So rarely will we ever have a data set that's going to exactly fall on that line, but it's going to get pretty close if its underlying distribution is normally distributed. Now, R has a couple of pitfalls that I don't want you to fall into. One problem that my students have frequently when they first start using R is that they overwrite built-in functions. For example, they've got a data set that they want to take the mean of, and they set mean equal to the average of their points in their data. For example, they might assign mean equals 5 plus 7 over 2 for their data set. Well, the problem is mean is a function in R that you can apply your data set to get the average out of. But as soon as you overwrite it, then R overwrites that function. And so instead of being able to use mean as a function, when you type mean, it gives you the average of 5 and 7. So be careful when you're using R to not write over built-in functions. The way that you can check that is by doing a question mark of the variable name that you'd like to use. So for example, question mark mean will spit out that the mean is actually a function that R uses. And so this clues you in that you may not want to assign it to a variable in your data. Likewise, things like C, which we learned above, is a variable that stands for concatenate or combine. So we wouldn't want to assign C to anything of our data because then we'd overwrite the combine function. Even things like T. T stands for transpose. And so we wouldn't want to use that as a variable name. On the other hand, we saw in this lecture widget. Well, R doesn't have a built-in function for widget. So it's fair game. So make sure you're careful when you start coding for the first time that you don't overwrite a built-in function. And do that cross-check just to make sure. Now, like a lot of my classroom students, you may come in not really knowing what to think about R. And I think, just like them, you're going to leave not only recognizing the usefulness of R, but also its incredible power.